Hey guys, it's Bad back again. I know it's been a long time. I haven't posted. Just been a bit busy with uni and stuff. Um, I've been meaning to get to a video and it's just been on my mind, but it's just been so hectic with everything. But now that I've finally got a breather, a lot of my students have been asking about graph questions and how ASA and GAMSAT assess those. And so I thought it would be good to make a video on giving you guys a graph question so that you can see how sort of what they expect, what sort of reasoning skills they expect, and how you should go about working through them. And I think obviously this is really important because, yeah, GAMSAT loves graphs, and you need to build the skills to interpret the graphs and make the relevant deductions to get to the right answer. And it's something that you get with practice, with obviously with the questions that you're given, or good quality questions, which hopefully um, through the one that I'll give you and walk through with you guys, it's going to be helpful. And hopefully you can pick up some techniques for yourself so that when you're doing graph questions, it's a bit easier. So I will walk through the question. I'll get it up in a sec, but uh, before I do that, if you want to get more questions and stuff like that, I would suggest subscribing to the channel as well as joining the Facebook page. So I've got a link to that. When I start sharing screen, you can see that. And that's the best way you can keep on top of the videos, because when I make the videos, I'll post them on the Facebook page first as well. So you'll always have access to it from there. Okay, so let's get right to it. Okay, so here's the question, guys. And oh yeah, before I get started, here's the link. I'll put it down in the comments below as well, and in the description, so that if you want to join, you can. But yeah, so here's the question. What we'll go through first is we'll have a read of the question, which is what I suggest all of my students. And we'll go through how you sort of read the graphs as well. I always suggest having a read of the stem just so you have a big, broad, overarching idea of how to do the question. It's really important because ASO often, like, in some way or the other, if you don't have an understanding of sort of what's going on in the STEM, it can make it quite difficult to answer the questions that ASA puts forward. So really important to read and at least have a broad understanding. So definitely read like this paragraph. So at least that's what I do, and I find that quite helpful. So I'll show you how I do that. So let's start from the top. So rains and drizzle are crucial for the self-cleansing process of the atmosphere. So we're told rain is important for self-cleansing. So the essence you need to know from that sentence, rain helps with the cleansing. And I find it good to underline just so that you can keep a track in your mind of what are the key ideas for every question, or keep in mind the key ideas for yourself. And I know when you get to the venue, obviously you're not allowed to underline, but hopefully it becomes sort of like a subconscious process that you're picking out the important information for yourself when you are attempting the questions. So that's something I've also found helpful when you are doing these questions. So let's keep reading forward. Scavenging of the atmospheric gaseous pollutants by cloud droplets. Okay, so you're scavenging for gaseous pollutants by cloud droplets is the result of gas absorption mechanism. Okay, so basically what they're saying, if you've got cloud droplets, trying to draw a droplet, that's a droplet, it scavenges pollutants. Scavenges means to get rid of, basically, or suck out, which is equivalent to getting rid of. So if you can understand that from that sentence, that's all good. Even though you might not exactly know what is the gas absorption mechanism. We might not know it. Concentration measurements of trace gases in the atmospheric boundary layer revealed altitudinal dependence of the concentrations. Okay, so concentrations of, you can ignore trace gases, just think of gases in the atmospheric boundary layer revealed altitudinal, that relates to how high you are. how high? Okay. Dependence of the concentrations. Okay, so when they measured the amount of gas, it relates to how high up above the ground you are. That's what I can understand from this sentence, roughly. I don't know exactly what trace gases are, but that's okay. It might come up later in the STEM and be clarified. I don't need to fret over it as long as I've got the big idea that, look, gases, the concentrations of gases change at different height levels. Okay, next line. Concentrations of gases which are not associated with photosynthesis, such as sulfur dioxide and ammonia, attain maximum value at the Earth's surface. Okay, so things like sulfur dioxide and ammonia, okay, they have a maximum value in their concentration at the Earth's surface. So if this was the Earth, you'd have the most here. What have they got? Oh, SO2, not NO2. SO2 and ammonia. And then decrease with height. So as you go up into the air, you're going to have less and less of SO2 and NH3. Ammonia and sulfur dioxide are indirect greenhouse gases. So basically, they're trying to tell you that they're pollutants. So that's probably the stuff you want to get out of your air or get rid of. And that's something that probably you should start sort of making the connection that it's probably something that the cloud droplets get rid of. Yeah? Indeed, ammonia plays a central role in the nucleation of atmospheric aerosols from the gaseous phase. Okay, so ammonia is NH3. It has a role in nucleation. I have no clue at the moment what that means, but that's okay. We keep moving forward. So we think about nucleation of atmospheric aerosols. Aerosols are usually gases, you know, like when you have your spray in toilet, that's an aerosol, you know, from the gaseous phase. So nucleating would probably mean if you have something in gaseous phase, it sounds like you're changing its state. And that could be to liquid, solid. I don't exactly know at the moment. So, but that's okay. You might not even need it to answer the question. So keep reading forward. And just already proof of the importance of reading forward. Remember about SO2 and NH3, or about the altitudinal dependence. They kind of explained it in the next line where they said sulfur dioxide and ammonia are actually maximum at the surface of the Earth or at the lowest altitude. So that's what I mean. Like if you read the next line, often it answers it. And sometimes it's not even relevant. So never stress too much if you don't fully understand every line. So since aerosols can serve as condensation, can serve as condensation nuclei. So that's where condensation, if you remember, is when you have a gas going to a liquid. So for cloud droplets, so aerosols can serve as condensation nuclei for cloud droplets. So they help the clouds to form basically, because they're helping the cloud, the aerosols or the gases are helping the gas become a liquid, or the cloud gas become a cloud liquid. So ammonia indirectly affects cloud formation, cloud lifetime. That and shouldn't be there. And at the same time, rain influences the height of cloud formation. Rain influences the height of cloud formation, cloud characteristics, because rain affects the vertical distribution of gases and aerosols. Okay, that is a lot. That's a lot. I feel a bit lost in those two lines. So it's okay if you, even if you don't understand it totally, just try and break it down into something that you do understand, you know? So in this case, since aerosols can serve as, I'll go back to that line about since aerosols. So since aerosols can serve as condensation nuclei for cloud droplets, ammonia indirectly affects cloud formation. Yeah, I'll just break it into two parts. So just understand that aerosols can help clouds to go from gas to liquid, and ammonia affects cloud formation, cloud lifetime, blah, blah, blah. At the same time, rain affects, just understand that rain affects cloud formation and like its traits. Because rain affects vertical distribution of gases and aerosols. Okay, there's a chunk of a lot going on. Even if you don't understand the full the full details, nitty gritty of it, that's okay. Just make sure you have the broad gist, which is what I've said about ammonia affecting, first of all, about aerosols helping condensation of the cloud, so going from gas to liquid, ammonia affecting cloud formation, and so does rain affect height of cloud formation and cloud characteristics. So yeah, just understand those three. If we need to refer back to it, we can always come back to it. So that's sort of the way you read this, and don't get too caught up. That's really important because we also have the graphs to read, and the graphs will tell us another sort of part of the story. Okay, the graphs are, I'd say, even more important. You have to pay more attention. And that brings me obviously to the graphs. And when you are doing the graphs, what you want to do is always look at your X, your Y, and what's inside. So U0, I have no clue what that is. Fine. If you don't understand, one of the other steps after you've looked at the axes is to look at the figure legend. But obviously looking at the axes, we don't even understand U/U0. So you have to read the figure legend, or the thing below this. So figure 1, dependence of scavenging velocity for gas absorption of SO2, because sulfur dioxide, by evaporating droplets versus distance from cloud bottom for various values of humidity. Okay, so this is distance from the cloud bottom. So this is 200 meters from the cloud bottom, 400 meters from the cloud bottom, 600 meters from the cloud bottom, so on, so on, so on. And that means that scavenging velocity is this thing here. That's what it has to be. It's scavenging velocity versus distance from the cloud bottom in meters. And the various values of humidity are these things. 100%, 97.5, 95%, 92.5, 90%. And each of them are represented by a different type of line. So 100% humidity is a solid line, whereas the very, very dotted line is 90% humidity. Okay? So we can just apply the same approach when we're going through the next graph. So again, look at your X, look at your Y. So your total altitude in meters up to 1,000. XG, we have no clue, so we're going to have to read the axes. Again, you've got SO2 here. Don't know what that is, but I'm not going to worry too much. We've got something about 1 and 2. So 1 is RH equals 70%, and RH was the humidity. So I'm assuming that's humidity. So 1 represents a humidity of 70%, and 2 represents non-evaporating droplets. And these different lines, T equals 0, 10, 20, 30, 40. I don't know what it means. So I'm going to have to read the figure legend. So let's have a read. So time dependence of sulfur dioxide distribution in the atmosphere caused by rain scavenging. So remember, the rain actually is part of self-cleansing. Remember here it says rain does self-cleansing. And if SO2 is a greenhouse gas, it's a pollutant. So the rain's going to get rid of SO2. So that's what's happening. That's what they mean here. So the time dependence of sulfur dioxide distribution in the atmosphere caused by rain scavenging. 1 is when droplet evaporation is taken into account, RH equals 70%. 2, evaporation of droplets is neglected. So this is evaporating. The main difference is this is evaporating, this is non-evaporating. That's the difference between 1 and 2. Xg is the mole fraction of a soluble trace gas in gaseous phase. So a mole fraction is just how much of it there is, basically, because parts per billion, if you're familiar from chemistry, it's a measurement of how much of that gas you have. And obviously, if you're considering in the atmosphere, it's in gaseous phase. You're probably thinking how much of that SO2. So like, for example, this this is probably 7.5 parts per billion SO2 when you're at an altitude of 0 meters. Whereas when you're at an altitude of 1,000 meters, you only have 4.0 parts per billion of SO2 at an altitude of 1,000 for the condition of, let's just say this black line. The black line actually represents both 1 and 2, but for the sake of 1, let's imagine it was 1 that's being represented, because technically 2 will also be this exact same line. And notice that's kind of different to this other one where 1 and 2 are separate. When time equals 0, both 1 and 2 overlap. That's something you got to be careful of. So yeah, so it represents the parts per billion of SO2. If it was 1, if you wanted to take 1, that's when we take into consideration droplet evaporation. Okay. And so you can just like notice a general trend that you have at the closer to the Earth's surface at 0 meters, you have more of SO2, which corroborates what you had in the passage, which is that at Earth's surface, you have the most SO2 and NH3. So that's making sense. Okay. So now let's look at another figure. So figure 3a. Dependence of scavenging coefficient versus rain intensity for sulfur dioxide washout for different values of growth constant K1 and K2. Okay, so let's have a look. Scavenging coefficient versus, so scavenging coefficient and 10 to the 4 per second, 10 to the negative 4 per second, and rainfall rate is R millimeters per hour. Okay, so scavenging coefficient 10 to the negative 4 per second. So I think it's like you're having scavenging like 10 to the negative 4 molecules of SO2 per second. That's sort of the idea I have, roughly around this, and it varies with rainfall rate in millimeters per hour. Okay, and you have different values of the constant K1, K2. Cool. K1's the solid line, K2 is the dashed line. Simple. Like there's not much to it. But there is, I like to pay attention to the trends. So I can notice that as your rainfall rate increases, you get more scavenging. Your scavenging coefficient gets higher. So just something to keep in mind. If you can pick up the trends as you go with graphs in GAMSAT, especially section 3, it's very good. So just keep that in mind. All right, let's look at figure 3b. Dependence of scavenging coefficient versus drizzle intensity. So scavenging coefficient versus drizzle intensity for sulfur dioxide washout. Washout means to get rid of the SO2, which is what we're doing here, for different values of growth constant, K1 and K2. Okay, so here's your scavenging coefficient again, but this time it's 10 to the negative 6. And this is for rainfall rates in millimeters per hour of 0 to 0.1. So it's very tiny. And that's why they call it drizzle. You know, this was rain because it's for a higher amount of rainfall. It's like 0 to 20. So that's why. Okay. Same idea, different K values here, but the idea is still the same. The more your rainfall rate is, the more your scavenging coefficient is going to be. Okay. Cool. So what else is there? One more graph. So again, it doesn't really matter, by the way, if you read your figure legend first, your axes, but you need to read all of those things to piece the picture together. And the essence should be that you can explain in simple words what's going on and what that graph's trying to depict. Like imagine if you were trying to explain to a friend, you should be able to explain it. That's the very key idea, okay? In terms of what this graph is showing, we've got the altitude again, we've got scavenging coefficient here on the x-axis, 10 to the negative 4 per second. Dependence of scavenging coefficient versus altitude for sulfur dioxide washouts, so getting rid of sulfur dioxide, by evaporating rain droplets where air humidity is 70%. So there's your 70%. Still don't know what that is, but I'm not going to worry. It's probably not too important until they specify it in a question. Now, rain duration is specified. What solid line is 1 minute, and so on, so on, so on. So like the next one's 10 minutes, and so on, so on, so on. The point that I'd like to take from here, again, try and notice some trends whenever you look at a graph. You can sort of deduce that if you look at an altitude of 0 meters, the longer your rain duration, so 1 minute versus 10 minutes versus 20 minutes, you have a higher scavenging coefficient. So here your scavenging coefficient is 1.5, but here it's like 1.6. And here it's almost I'd say probably 1.75, something like that. So it's just getting higher and higher. So that is something you should be aware of. Okay, take note of the trends. So we know that as the rainfall rate here, why is my pen giving up on me? Always. So as rain duration increases, your scavenging constant increases. And from the previous question, as your rainfall rate increases, then your scavenging coefficient increases. So if you have greater rainfall and for a longer period, you're going to scavenge, your scavenging coefficient goes higher, which means you would scavenge more sulfur dioxide out of the air, which is good. You want to get rid of those greenhouse gases. And that's why rain is a self-cleansing part of the whole, picture of the world. So take care of that. All right. You could also look, if now we just focus on rain duration of 1 minute, so this line here, the solid line. If you notice, at an altitude of 0, the scavenging coefficient is 1.5, but at an altitude of like 1,000, scavenging coefficient's all the way up at 2.4. So your scavenging coefficient increases with altitude. Do you see how you can generate some sort of patterns? That's what you should be trying to do with these graph questions, or at least it's good to have an idea of the patterns. It definitely helps in terms of understanding things. Even if, I think generating these patterns helps you feel like you're more confident in terms of understanding the graphs. But even if you just get the broad gist that, look, scavenging coefficient varies with rainfall rate, and altitude varies with scavenging coefficient, that can help as well. But for me, I find that it's better to have some sort of trends to sort of help understand the graphs. And essentially what you want to know, you should be able to just, like I said before, make sure that you can explain the graph to a friend. Like, for example, for figure 4, you should be able to say that, oh yeah, this is telling how your scavenging coefficient changes with altitude, and it also varies with your rain duration. Obviously, the next step up was to do what I did, which is to say that, well, the way in which it varies is that the higher you go, the higher your scavenging coefficient is going to be. And the longer it rains, the higher your scavenging coefficient. That's like the next step. So yeah, just helps in your interpretation of things. But yeah, make sure you can explain the graphs. That's really important. And understand what they're talking about. It makes answering the questions easier once you get to them. Okay, so let's actually get to the questions. So question 1. If the rainfall rate is 10 millimeters per hour for a K1 of 6.36 times 10 to the negative 6 centimeters, the rain continues for a period of half an hour, which is 30 minutes. Again, if I'm underlining here because often ASA gives a lot of the information they give in the actual question actually helps direct you to what you need back in the STEM. So you should definitely be underlining so that you know what to refer back to in the STEM. So, and the rain continues for a period of half an hour, so that's 30 minutes, like I said. So at a humidity of 70%, what would the expected altitude be? Okay. A lot of information, but I've underlined the key numbers that I want to work with. So I think about K1. Where have I seen that before? So that K1 There's actually two spots I see it. One's here and one's here. 6.36 times 10 to the negative 6 centimeters to the power of -1. But rainfall rate is 10 millimeters per hour. Now, the only place where it is 10 millimeters per hour is in this graph, not in this graph, because this is too less. Look, it's only from 0 to 0.1. Not enough. We need to go here. And then if we go here, 10, draw a line across, it's roughly at 2.2. It's 2.4, 2.6, 2.83. So 2.2 is your scavenging coefficient. Now, if your scavenging coefficient is 2.2, we've deduced from these two pieces of information that your scavenging constant is this. Oh, sorry, scavenging coefficient. Okay, and the rain continues for a period of 30 minutes. So which graph talks about the period of rain? It's not 3B, not 3A. 2 talks about 30 minutes. It could be this, the duration of rain. But there's also another graph which talks about duration of the rain, which is graph 4, 30 minutes here. Now, given that we've found the scavenging coefficient, to pick between these two graphs, which one has the scavenging coefficient? Figure 2 or figure 4? Well, we can't see the scavenging coefficient on figure 2 anywhere, so it's probably going to be figure 4. So yeah, there's your 2.2. Now go up to the line, which is for half an hour. So 10, 20, this must be 30. So if we draw across, that's 300. So that would be 250. Okay, so your answer here is 250. That's what your expected altitude is going to be. So it's a bit of like each step depends on the previous step. So that's sort of what you can expect in sort of a GAMSAT style question where you have to work out things and connect the dots up for yourself. Because it's like a puzzle, All right, question 2. Let's do the same thing. So which of the following correctly describes the trends? So the key word here is trends with regards to the scavenging of SO2. Okay, let's read option A. The removal of SO2 increases with greater altitude. With greater rainfall and is higher with greater rainfall duration and is greater at a higher altitude. So finding the trends actually came in handy. It's not always they can ask a trend question, but in this case, it's come in handy because, well, we kind of made a little bit of a note of it. So yes, greater rainfall causes greater removal of SO2. And yes, the greater the duration of rainfall, the more cleansing, so you get more removal. And remember, with regards to the removal, are we going to have greater removal? Yes, because you have a higher scavenging coefficient. So good, yes, you do have a greater removal at a higher altitude. That's all good. The mole fraction of soluble SO2, okay, now this terminology sort of comes up here. I remember this from here, mole fraction of soluble trace gas in gaseous phase. So it's probably something to do with this because that's the only place where mole fraction is mentioned. So the XG is, so basically the mole fraction of soluble SO2 in gaseous phase is lower at lower altitudes when there is droplet evaporation is considered. Okay. So they're asking, is XG lower at lower altitudes? Okay. So let's look at the trends. No. XG was 7.5 at a lower altitude. It was higher at a lower altitude of 0 meters compared to when you're at an altitude of 1,000, it's 4, which means it's lower at a higher altitude, which makes sense, right? Because we were told in the stem of the question that the higher up you go, the less of SO2 you have. So obviously you'll have less of a mole fraction. A mole fraction is basically how much, it's a fancy way of saying how many moles of SO2 are there in the air, which is composed of a lot of moles of other things. So obviously, if you have less of SO2, then you're going to have less moles of SO2 in the air and a lower mole fraction. So everything, we need some option with all the same starting points, but the last point needs to be it's higher at lower altitudes. The proportion is higher at lower altitudes because you're near the Earth's surface. So I think that's C. The removal of SO2 increases with greater rainfall and is higher with greater rainfall duration and is greater at a higher altitude. The mole fraction of soluble SO2 in gaseous phase is higher at lower altitudes. So yeah, the mole fraction of soluble SO2, or the Xg, is higher at lower altitudes. So remember, at an altitude of 0, the Xg is 7.5. That's higher. Oh, and there was something they said, when you consider droplet evaporation, which means that was 1, if you guys remember. That's when evaporating is taken into account. See? It says it here. Okay, so that's this number 1. That's this number 1 here. So obviously it didn't matter because number 1 and 2 lines are the same, but yeah, in this case, the answer should be C. Can't be B because the removal of SO2 decreases with greater rainfall. No, you remove more SO2 with greater rainfall. Okay, now let's do question 3. What would be the expected scavenging velocity by evaporating droplets at a humidity of 85% and a distance from the cloud bottom of 1,000? So scavenging velocity is unique in that it was only mentioned in the very first figure. If you think back to it, remember scavenging velocity and distance from cloud bottom, that's unique to figure 1. So I know I have to refer back to figure 1. So what I'm trying to get at here is always try and use what the question is asking to help you find what you need to look for in the passage. So especially with graph questions. So what would be the expected scavenging velocity? What would be the expected scavenging velocity by evaporating droplets at a humidity of 85%? So distances at 1,000 meters, they're asking us to find the U over U0 because that's scavenging velocity. So here's your 1,000. I think I should use a different color. So you have to look at, here's your 1,000. Now we're trying to find U/U0 for a humidity of 85%. 85% is very, very different to what we've got here. It's much lower. So obviously you could think it's going to be much lower by the time we get to 1,000. Or sorry, by the time we get to a humidity of 85%. But the way I do this, right, is I'd first figure out how much it's, like you can see that every time your humidity drops by 2.5%, it's dropping by 2.5 increments. So I try and notice how much it drops each time. And just looking at it, when you have a humidity of 100%, you're here, then 97.5% you're here, then 95% you're here, then 92.5% you're here, and 90% you're here. Okay, so looking from, you start at 1 as your scavenging velocity, then your scavenging velocity goes down to about 0.9. I chose this point because it's a 0.1 decrease exactly. And it corresponds with going down from 100% to 92.5%. So 7.5% decrease in humidity. So if you look now, we need to get to 85%. So if at 92.5%, after a 7.5% drop in humidity, you lost 0.1 of your scavenging velocity. That means that if you dropped another 7.5% in humidity, to get to 85%, your scavenging velocity would be another decrease of 0.1. So you'd be at 0.8 because 1 minus 0.1 minus 0.1 is 0.8. So that is where you get 0.8 from. Cool. Oh, I didn't know I've given you guys the answers there. Shouldn't be looking at them. But that is how you do that. Okay. Now, if you look at the other question, the last question, use that same approach that we've developed. So for an altitude of 300 meters and a scavenging coefficient of 2.1 times 10 to the negative 4 per second, and the xg is 4.8 parts per billion, which conditions could give rise to these values? And we're talking about rainfall of duration, just looking at the options broadly. Rainfall of duration where evaporation of droplets is taken or not taken into account. Okay, a lot of information. Again, xg is unique. I remember that was only mentioned in one of the figures, which is this one, figure 2. So xg is 4.8, they've said. 4.6, 4.7, 4.8, so something around here. Okay. Anyway, so that's there, 4.8. Yeah. And then if you look at the next bit, so we've got altitude of 300 meters, scavenging coefficient of that. Okay, we need to go to altitude and scavenging coefficient. Okay, this is a good graph for altitude and scavenging coefficient. So altitude of what? 300. Oh, there's 300. Okay, so 300, and what did they say? Scavenging coefficient of 2.1 times 10 to the negative 4? Was it? Yeah, so that is here. Okay, so 300 meters, 2.1 times 10 to the negative 4. You're falling on the line, which is t equals 20 minutes. So you can deduce that the rainfall was for 20 minutes. Okay, and then we go back to our graph. So we know we had to focus in figure 2 on t equals 20 minutes. So t equals 20 minutes, which is, this was 0, this is 10, this is the 20-minute line. Okay, and remember our altitude is still 300. That doesn't change. Okay. So we're focusing on the intersection with these two lines. So hold on. Actually, one thing we can eliminate is that the rainfall duration is of 20 minutes. So it's either A or B. Now, if xg is 4.8 parts per billion, which conditions could have given rise to these values? So we need to figure out whether evaporation of droplets is or is not taken into account. So let's have a look. Where is it? So altitude 4.8's there, boom. So it looks like it happens in the case where condition 1 is satisfied, and condition 1 is where droplets evaporation is taken into account. So should be B. Okay. So yeah, that's it for those set of questions. Hopefully you guys found it helpful. And yeah, just subscribe, and if you have any questions, just let me know in the comments below or otherwise. Well, good. Thanks so much.